In this video, we're going to revisit the graphs of quadratic functions. Just a reminder, make sure that you listen and pay close attention so that you understand what you're listening to, and then pause and take notes on what you need to write down. You won't necessarily have to write down everything you see on screen. Quickly, let's revisit the parent function for quadratics, y equals x squared. I have the table and the graph of the parent function on the screen, which hopefully you recognize already. It's pretty easy to identify the vertex of the parent function. That's the coordinate 0, 0. And the axis of symmetry is also pretty easy to identify. That is the line x equals 0. It's important to point out that that x value for the axis of symmetry is the same as the x coordinate of the vertex. Now, some of you might guess what we're about to do next. And it's the same thing we did with square root functions and cube root functions and absolute value functions, which is look at transformations. So we have the ability to do some transformations here using the same format we had before. We can have an a in front. We can have h subtracted from the x inside the function being squared. And we can add a k. And just like anything else we've seen for all the other functions, the h is the horizontal shift, and the k is the vertical shift. Nothing here is new so far. This is all repeating what we learned in previous units. But if I imagine a function, say y equals x minus 2 squared plus 3, as we've seen before, the horizontal shift will move it forward 2 units, and the vertical shift will move it up 3 units. Now, that will move all of the points, of course, but I want to focus on the vertex in particular, because since the vertex started at 0, 0, if we move it to the right 2 and up 3, the new coordinates of the vertex will be 2, 3. And so because that 0, 0 is the starting point, and we've moved it h to the right and k up, the new coordinates of the vertex are just h, comma, k. And that's a big deal, because that makes this form of the quadratic function very, very, very useful. So here it's written a little bit more formally. We call that function, the form of the function, vertex form. And it looks just like the transformations we saw in previous units. Sometimes you'll see this called transformational form. But what's really important to note here, the big takeaway, is that the h and k from inside that vertex form are the coordinates of the vertex. And because the axis of symmetry is just the x value of that vertex, that's the same as the h. What that means is if you see a quadratic function in vertex form, it is super easy to identify the vertex and the axis of symmetry. In question number 1 here, x minus 3 squared plus 12, the vertex of that function will just be at hk, 3, 12. Of course, it's a coordinate, so I write it in parentheses. The axis of symmetry will just be x equals 3, the x value of the vertex. That's it. For number 2, the fact that the a is 5 means the parabola will be steeper, and that will certainly impact the way the graph looks, but will have no impact whatsoever on the vertex or the axis of symmetry, which are still going to be found just by looking at the h and k. The vertex is at negative 22, negative 52. Do notice that plus sign here when we're expecting it to be h. X minus h, when there's a plus sign in there, that means the h itself must be negative. And so the axis of symmetry is also at x equals negative 22. Now that's the great thing about vertex form. It's so easy to find the vertex. The x and y intercepts are a little bit trickier, and you're not commonly asked for that, but I will show you it's not that hard to find the x-intercept, or the 0, when you have an equation in vertex form. What that means to find the 0 is find the x value that makes the y 0. So if we write that equation out as x minus 3 squared plus 12, in order to solve that, we will get the x by itself. This will look a lot like what we do when we complete the square. Subtract 12 from both sides. And then take the square root of both sides in order to get the x minus 3 out of those parentheses, out of that square. Now, doing so will introduce an imaginary number, and that's fine. There's nothing wrong with imaginary numbers. We also will have to remember the plus or minus. And so x equals 3 plus or minus the square root of 12i. And that would be, now I can't call it the x-intercept because it's not real, but it is the 0. Just because it bothers me, I will simplify that square root of 12 also. 2 times the square root of 3. One other thing that we have to be able to do for this is switch from standard form to vertex form. And so we'll walk through the process for how to do this. It should sound familiar because it's a lot like what we did when solving quadratics. Our first step is to isolate the x squared plus bx. Now this is possibly the first time we've done this. When we start solving for x, when there's also another variable involved, I can't just pretend that y is not there. So isolating the x squared plus bx does mean move the 5 over to the other side. But that y doesn't become a 5. It's still there. It's y plus 5 equals x squared plus 8x. So I've isolated the x squared plus bx. You might guess the reason to do that, but if not, that's fine too. The reason why we like x squared plus 8x by itself is because it's very easy from there to complete the square, which will help us get to the perfect square that we see in the vertex form, the x minus h squared. So if we've got x squared plus 8x, what number do we need to complete the square there? Well, that is b over 2 squared. And so in this case, that's 4 squared. So that's adding 16 to both sides. Still have that y there, hasn't gone away. I can add 5 and 16, and the other side is now my perfect square. And what I'll do now, in this case it's really not that hard, I'll get the y by itself again. So I will subtract 21 from both sides. X plus 4 squared minus 21. Now our equation is in vertex form, which makes it really to identify all of the important components. I can start by saying the vertex is at -4, -21. The domain we know is all real numbers because it's a quadratic. If the vertex gets as low as -21 and the parabola is opening up because the a is 1, the a is positive, we can say the range must be from -21 to infinity. We also can picture a parabola with a vertex at -4, -21, which means the function is increasing from that vertex, which happens when x is -4, until forever. And the function was decreasing from -infinity until -4.